E total. That's one equation. And then what else do we need? Minus h bar squared over 2m, 1 over psi, partial squared psi with respect to x squared, plus v of x, or v of x. That also has to equal e total. Okay. Let's do this one first. Okay, what am I going to do to this one? Going to multiply through by.
What are you going to solve for?
I'm not going to try to solve this explicitly. I'm going to get it into a function form. So maybe I'll just. I'm going to multiply everything through by side. And when I multiply it through by side, I know minus h bar squared over 2m partial squared psi with respect to x squared plus v of x times psi equals e total times psi, which I can rewrite as minus h bar squared over 2m partial squared with respect to x squared plus v of x times psi equals e total times psi. And what do I recognize all this stuff as? This is what? Kinetic energy. This is essential. So what does this represent when I add those two together? The Hamiltonian. So this is H0, my basic Hamiltonian, times psi equals E total times psi. Okay, remember what we started out trying to solve is H psi equals IH partial psi with respect to t. This was called the what equation?
The time independent.
The time with Schrodinger's time dependent equation. What do we have down here? The time independent equation. Okay, so what's the big relief that we've got now by solving this instead of this? How many variables do we have to solve for over here? Two. What two? Position and time. How many variables are we solving this partial differential equation for? One. So have we made our life a little easier?
Yeah.
We have. Alright, so going from the time-dependent equation to the time-independent equation, we've eliminated time. Alright, let's see what the time equation comes out to look like. So come on over here. How would I go about, what would you do here? Can I solve this? Maybe I can solve it.
Just get back to what we're just.
Yep.
I was both lowercase size.
These are lowercase size.
So you could cancel them out?
This is the eigenvalue problem. Remember? This is the total energy, as if it were particle times psi, equals E total, like a eigenvalue times psi.
It is less nice.
It's an operator. This is what it really is, Nino, right? So this is asking you to solve this differential equation for psi that makes all this work. But the kicker is that it's only a function of one variable, x. It's no longer a function of time. And so it's an easier problem to solve.
How does what you're doing right now connect to this? Like what we do with it?
What's that?
How is this, what you're doing right now connecting to this?
Out of here, I argued that you had to have a constant.
Right.
That constant for both equations was E total, so there it is.
Okay.
The x part equals E total. And over here, the time-dependent part is equal to E total.
And that's where you get the E equals blah, blah, blah.
Yeah, so let's solve that. Let's go through it. What's the next step? Let's look at the time-dependent part. Okay, well, let's do some algebra. So, what do I have that? Let's go on I h bar. Yeah, we'll go partial g over g equals E total. And instead of using partials, because now, I don't have to use partials anymore. Yeah, so nice call. Good call, Mike. Is that I could equally well, and I should, write this as d squared instead of using the partial, because now it's only a function of one variable x. So I don't have to use partials. All right, very subtle stuff, right? So this could be d squared, d squared, d squared, d squared, right? Everybody see that? That's subtle. Okay, and over here it could be dg, dt, so dg, d total dt.
Why are you able to make that just a regular derivative?
This is a total derivative. A little d is a total derivative.
Yeah.
And a partial is a partial derivative.
Right.
And so if I only have a function,
This
this is a function of one variable.
Position, yeah, we're just position, yeah.
Yeah, then when you find this thing, it represents the total derivative as opposed to the partial derivative. So it's nice mathematically to be consistent when we should do that.
At this point, we can divide both sides by IH bar.
Yeah, so I would do that. I would say dg over g equals 1 over I h bar e total dt. That equals minus I e total over h bar dt. dg over g. And David, as you mentioned, I would integrate both parts, divide on both sides. Do an indefinite integral. What's the integral of this? Log g equals
I e total over H
plus or
bar
minus I minus I e total over h bar times plus c, because I solved the indefinite integral. I didn't put in limits, right?
Why did we make the negative sign there?
Because I had I in the bottom, and I multiplied top and bottom by I. Okay, so I went I over I. So this becomes I squared. I squared is minus 1, but I get I on top. My whole rule of thumb with complex numbers is, I know what a complex number is when I is in the numerator. But I don't know what a complex number is when I is in the denominator. So general rule of thumb is I get my i's out of the denominator and put them in the numerator.
It's like dealing
That's
with
good,
radicals.
good.
Yeah, it's good for me to do it that way. All right, so how do I solve for g? G of t equals
E power e to the negative I e total over H bar t plus
okay, plus c, right, which equals
e to the c.
e to the c, and e to a constant is a constant. So it's going to be some constant, c, e to the minus I, e total over h bar t. Right?
Is that constant in front what you get when you normalize it?
Okay, so exactly. So here's the scoop. We know to have Bourne's probabilistic interpretation of quantum mechanics, so that when we integrate all the d probabilities over all whatever space we're in, what are we going to get? 1. So what do we have to find to make our probabilistic interpretation work? The normalization constant. All right? And so for now, I sometimes don't even write it in. I just leave it like that. Because we're going to, later on we're going to find out what it is. Right? We're going to find out what the normalization constant is later on. Everybody okay? Okay. Okay. Now, again, what did we were trying to solve for this. We assumed a solution equals g of t times psi of x. What did we find out that g of t equals?
E to the I negative I e total of H bar t.
Yeah. And then what aside? We leave psi of x. All right? Little psi of x. And then how do we solve for little psi of x? What do we solve?
Time independent.
We solve Schrodinger's time independent equation. Everybody got it? Yep.
I kind of missed the jump from when we were doing position and everything. Why do we go into the time-dependent piece over there?
Because our goal from the very beginning, we have to solve Schrodinger's time independent equation. All right? But what we say is that it's very messy because it's a function of two variables.
Right.
So what we're going to do is we're going to try to do separation of variables to make two easier problems.
Oh, touch up, all right.
And it turns out that the time part of the
That
problem
was just.
has an answer.
Yeah, it's just that,
It's
right,
just
and then the
an
other crap was the position piece.
Yeah,
All right.
and then this other doesn't have an answer, but we can find it more easily by solving the time independent
All
equation.
right, cool, thanks.
Okay, so it sounds like you guys are getting the gist of this. And this is all we have to do.
So then, when you solve the side, you're just gonna solve the side.
Yeah, so now that's it. We have size, but how many sides do we have? When we solve the time independent, how many sides are we going to have?
Seem to have one on each side of the equation.
No, but I said it over here on this part of the board. The solution to Schrodinger's equation, time independent equation, will have an infinite number of solutions, psi n. So if I wanted to write it in, I would write it in as psi n. Right? They're going to have an infinite number of solutions. All right? And what's really neat about these infinite number of solutions?
They form an
They form a
infinite
complete
basis.
set.
They're just wonderful. All right? They're complete, right? And they form a complete basis set of function space. These solutions, they have to be square normalizable, right? Why do they have to be square normalizable?
So that they can equal 1 for a probability.
Okay, so that when you do the integral of psi star psi dx, and you add up the little tiny d probabilities, you get 1. That's called square normalizable function. By the way, this will have solutions that aren't square normalizable. And what do you say about the non-square normalizable solutions?
Doesn't
Not
represent
really.
something in nature.
It
Doesn't
represent something that we know of, right? Because what we know of add up to 1 when you add up the probability. So what do you do with those solutions? Don't use them. Okay? So we're going to use the square normalizable solution. Those square normalizable solutions have all the properties of vectors, the basis, like the vectors I hat and j hat. All right? So therefore, you have this great basis set. You go back to our original problem. This is En, psi n. Right? And these become essentially our what? These are our bigger basis functions.
When you're at, if you scoot through it for a second, if you have the Hamiltonian psi, E total psi, mathematically, this could be an ignorant question, it just looks like you can cancel psi n, both sides. Doesn't it?
Well,
Like right here?
Yeah.
Yeah, sure. Go ahead. And what have you done? Nothing. But what does this represent? This. And this represents a partial differential equation.
But I'm just saying, like, it looks like you can cancel those two things, the sides.
Right. This is an eigenvalue problem.
Right, so that would give you nothing, and you have to have a side in there.
Well, you say it's an eigenvalue problem, and if you wanted to approach it like that, like an algebraic problem, then you would do it like you would say, yeah, this represents total energy on both sides of the problem. But this represents a partial differential equation.
All right, that's good clarification.
What's this last piece? We can have the summation here, the psi of x. What's
So this is Cn. Alright.
it's not a function of time either. Right?
That will not be a function of time. Yeah.
So that's Cn, that's the normalization constant for each unique side.
Here, it's not normalization. Yeah, in a way it is normalization, but here's a better way to look at it. Okay. Remember what I said? These things have all the properties of like bases, like I hat, j hat, and k hat. So in vector space, if you had f, you would have f of x in the I hat, and then you would have f of y in the j hat direction. Right? With this vector f equals f of x in the I hat plus f of y in the j hat. Everybody agree? Right? And what would you call these things? Have you guys heard me use the term projections? So this f of x equals projection of f onto this basis. F of y is the projection of f onto that basis. So what might you be tempted to call CNs?
projections onto another basis?
Pivot projections of psi total onto each basis. How many basis vectors do you have?